So let's move on to the next part. So before moving on to the next part, uh, I wanted to clarify that I had to re-record the second part because initially I made a mistake. Then one of our students told us that in simulation he was getting something else. So yeah, then I missed a point. That's why my answer was not coming out. So I had to re-record this part. So yeah, I will explain what mistake I did. So in the second part, right, what they're telling us is to plot the output voltage when my time period is much less than RC. When your time period is much less than RC, it basically means that this 5-volt source you cannot assume as DC anymore. 5 volt is there, your capacitor will not be able to reach 5 volts because we don't have enough time. The time constant is much greater. So to charge to its full value, let's say this RC, right, is something 4 milliseconds and this time period is something 4 microseconds. So the 5 volt waveform is only present for 4 microseconds and it will go to -5. But to charge the capacitor, I need 4 tau time, that is 16 milliseconds. That is very large. So my capacitor will never be able to fully charge to 5 volt or -5 volt. But what will actually happen here? So I will explain you briefly what happens in the steady state. If you want to understand in the transient state what happens, you need to go and watch this video. I will not be able to explain what happens during the initial first few cycles. I am talking about after 100 or 200 cycles at steady state, how will the capacitor voltage behave like. If you want to understand the initial few cycles, what will happen initially, you have to go and watch this particular video. Okay, so in general what happens is if the input is stable, then my capacitor will reach steady state. If the input is stable and it is a first order circuit, the capacitor will certainly reach steady state. Now here, what does steady state mean? Steady state, because the input, you cannot assume it as DC, it is constantly changing. This input will also keep on, this output will also keep on constantly changing. But what will be constant? The constant will be the average value of the capacitor voltages. This voltage and this voltage, both of these voltages will be constant. There is a derivation. So in steady state, how does my capacitor behave? In steady state, my capacitor behaves as open circuit. But in reality, in this circuit, capacitor will not be fully open circuit or fully short circuit, right? Capacitor, the average value of the current across the capacitor will be 0. Then only it will reach steady state. This is a very important condition, and this condition I have taught in this particular video. How it came into action, the proof, the derivation I have explained in this particular video. If the circuit is stable, then the average value of the capacitor current will be 0. If the average value of the capacitor current is 0, that means on an average we can assume this to be open circuit. So if I assume this to be open circuit, this to be open circuit, then again we can come back into the same solution, that current through here is 0, current through here is 0. That means current through the resistor also will be 0. That basically means the average current across the resistor is 0. If the average current across the resistor is 0, what will be my resistor average voltage? It will be average current into the average resistor. So this will be 0. And if the average value of the voltage across the resistor is 0, that means the average value of the capacitor, because it is in parallel, this capacitor, let's assume this as C1, this VC1 average also will be 0. Now what about your VC2? So if I write a very simple KVL, you will see that your Vin equals to VC1 of t plus VC2 of t. This is my V input of t, right? So if you take the average throughout this equation, this will be the, we can take average. How to do average? I hope you know. This will be V in average will be equals to, VC1 average plus VC2 average, right? So of course we know VC1 average is 0. What is VC2 average? VC2 average is nothing but V in average. What is V in average? The average value of this particular waveform is nothing but, what is average? Average is area under a time period. So area under a time period will be basically -5. We are starting from -5 into capital T by 2 plus 5 into capital T by 2 divided by capital T, right, which is equals to simply 0. So your C2 capacitor average voltage is also 0. Average is 0, not the instantaneous. We are talking about average. Now let's come back to our original circuit. So we certainly know that the average values of both capacitor voltages will be 0, right? Now let's come back to our original circuit. So our original circuit was this. Let us take the first case. Assume that the capacitors were initially uncharged, and at t equal to 0 plus, I'm suddenly applying here minus 5, right? Before it was 0 volts only, suddenly I'm applying minus 5 volt. If I'm suddenly applying minus 5 volts, what will happen? I have a R, I have C, so what will happen? They will be charged initially because both of them will behave as short circuit, right? KVL will be violated. So this is C, this is C. No current will flow through here because the other two are behaving as short circuit. No current will flow through here. So the voltages developed across them will change instantly to minus 2.5, minus 2.5, and an impulse current would flow. So that is what will happen at t equals to 0 plus. Due to the minus 5 volt, this capacitor will be charged to minus 2.5 instantly, right? Sudden change will be there. Capacitor voltage will certainly change. Next, what will happen? Next, obviously, this capacitor, top capacitor, will try to discharge through this resistor. So the voltage of this capacitor will reduce and voltage of this capacitor will increase because the sum of the voltages of VC1 and VC2 must be same if I apply KVL. So this capacitor output voltage will increase. So it will slightly increase, right? Minus 2.5, it will try to go towards more negative value, not increase, sorry, go towards more negative value, okay? But do we have enough time? I have already told you that this capital T is 4 seconds, 4 microseconds, and this RC is 4 milliseconds. To reach steady state, I need how much? 4 RC? So not 4 RC, sorry. This is 2 RC, right? 8 RC actually. I need 8 RC. So 8 RC would be 32 milliseconds, and my minus 5 volt voltage is there only for 2 microseconds. T by capital T by 2. So we don't have enough time. So the voltage will try to go towards minus 5, but obviously it will not be able to go to because we are providing minus 5 for a very small amount of time. So our voltage will be something like minus 2.50000001, something like that. Okay, we are not providing enough time for the capacitor to go to minus 5. Then suddenly plus 5 is coming. The moment when plus 5 comes, and I have told you roughly the capacitor voltage will be near around 2.5 volts, minus 2.5 volts, right? So roughly the capacitor voltages are near about minus 2.5 volt. Again, if you apply the KVL, here you will see KVL is violating. Plus 5 is equals to minus 5, which is not possible. Again, another impulse current would flow, which will suddenly change the voltages of my capacitor to plus 2.5 to plus 2.5 volt. So these will be the voltages of the capacitor. Again, what will happen? Again, the top capacitor will try to discharge through this resistor. This voltage will try to be increased. It will try to go to 5 volt, and this voltage will try to go to 0. So again, I will suddenly change to 2.5. Then the voltage will try to go to 5, but I don't have enough time. So again, next time minus 5 would come, and this time when minus 5 comes, again the same condition. If minus 5 is there, KVL will be violated. How? So I will have minus 5 over here, and this is plus 2.5 plus 2.5. Again you will see KVL is violated. Minus 5 is equals to plus 5. So hence there will be impulse current, and they will charge both the capacitors to minus 2.5, and this will follow. This will keep on repeating. So as such, there is no transient for this particular example. There is no transient for this particular example. The waveform is repeating from t equals to 0 plus itself. And if you notice, the average value of the voltage waveform is simply 0. Average value of the voltage waveform is simply 0. average value of the voltage waveform is simply 0. Okay, which is again proved from here as well, and the complete derivation is present on this lecture. You can go and watch this. What about the current, sir? Can you think about the current? I will give you some hints. Obviously, if the voltage is suddenly changing, there will be impulse. Here there will be one impulse. Here there will be one impulse. Here there will be one impulse. If you see, and then the currents will be what? Because the voltage is increasing, the current will be slightly reducing. Okay, you can tell me. But what I want you to write down in the comments below is what will be the area of the impulses that I will observe at half time periods, capital T by 2, capital T, 3t by 2, is the magnitude of the area at different time periods of the impulse. Are those same or not? And what is the exact value of the magnitude of the impulse? I want you to write down in the comments below and let me know. This is a very good question actually. Not a general pulse response. This particular question I had not covered in the course itself. That's why I had to take an extra separate video and cover it. So if you did enjoy this video, hit the like button and share it with your friends. I will see you in the next video. Until then, happy learning.